Hey, welcome everybody. Happy Halloween. I'm going to be telling you about the Tropical Atlantic Currents Observation Study, or TACOS. And this is a study that we started in the tropical North Atlantic, and it's augmenting one of the Parada moorings. And this schematic here, let me get my my pointer. This schematic here is showing you the Parada Ray, which is a collaboration between France, the United States, and Brazil. And the U.S. contribution to the U.S.-led contribution to the Parada Way, which is funded by NOAA, are these blue symbols here, which is the Parada Northeast Extension. And our TACOS program is overlaying on the 4 North 23 West mooring. And Parada has been in the water. It's the 20th anniversary of Parada. And the P&E moorings have been in the water for 10 plus years. And the idea, one of the main drivers of this observing array, is to measure coupled ocean-atmosphere interactions, and to do those on diurnal to intraseasonal to seasonal to interannual timescales. So we have this amazing data set of moorings that have air-sea fluxes and ocean temperature salinity measurements. Okay, so why TACOS? Why do we need current observations at 4 North 23 West? This region, it turns out we don't have very many direct measurements of the velocity, and it's because the equatorial region is particularly difficult to sample with some of our traditional velocity techniques. When you deploy surface drifters, because of the background circulation, this shows you the distribution of surface drifter data on the upper left panel. You see the trajectories of drifters. You see that there's not very many sensors at the equator, because when you deploy them there, it's not for a lack of trying, the circulation quickly moves them away from the equatorial region. Additionally, if you deploy them north of the equatorial Atlantic cold tongue front, the right panel is showing you, the black curve is showing you the cold tongue front. We deployed a drifter just to the north of that. It follows the front and it's not crossing the front. So there's, drifters are a tremendous tool, but in this region, we don't have enough observations. Associated with the Parada program and a lot of other field programs in this area, we have shipboard ADCP and lowered ADCP cruisers, along with hydrography. And so we have sections of the velocities that are snapshots, and if we average them, we can get a sense of the mean circulation. And they provide very high resolution, but you need many samples to avoid aliasing from eddies and high frequency signals. And because of the way acoustic Doppler current profilers measure, you have this blind spot in the upper 30 meters. So there's little information, direct measurements in the upper 30 meters. Satellites provide amazing data. You can use geostrophic assumptions and wind-driven and Ekman assumptions to get what the surface currents look like all over the globe. But to do that, you have to divide by the Coriolis parameter, which vanishes at the equator. So you usually, when you use these products, they blank out the region from 5 south to 5 north, and so you don't, or they have to make some assumptions between 5 south and 5 north, so you don't have direct velocity measurements there that don't require a lot of assumptions. Okay, so this is why we need, if we want to look at the velocity in the upper 100 meters, this is why we need moored current measurements. Okay, so this brings us to TACOS. What we did was we deployed in March 2017 at the 4 North 23 West Parada mooring. The right panel is showing you what that mooring looks like. This is on the next generation of the Parada mooring, which is a T-flex mooring. And what it has is a standard MET package, and it has, on the right panel, you see these sort of red lines that show you TC and T. Those are temperature and salinity measurements at various depths down to 500 meters. And what we did for TACOS was we took the existing 10-year record of Parada measurements at 12 meters, and we augmented those. So we added 10 more current meters distributed in the upper 87 meters of the water column, with 5 meter spacing in the surface mix layer, expanding down to 10 meters, and then finally 20 meter spacing at the bottom. Okay. So from that, we're going to measure the near surface ocean currents and the vertical shear. So the difference between the currents at those levels. And the reason why we want to do that, what is our motivation for doing that? As you may know, hurricanes are quite active in the Atlantic, this year being a specifically active year. And so in the Atlantic, you have hurricane activity and you have strong rainfall over the neighboring continents that are strongly impacted by ocean atmosphere interactions in the Atlantic Ocean. So to be able to better understand those ocean-atmosphere interactions, we want to know what the vertical variations are in the upper ocean velocities, because they can impact upper ocean temperatures, salinities, they can impact ocean fluxes, mixing turbulence, and air-sea fluxes. So if you want to understand ocean-atmosphere interactions, velocity variations and how they vary with depth are important. But on the time scale that we need to be observing them, we want to have the ability to observe them from diurnal to intraseasonal to seasonal to interannual timescales, because we want to understand how those upper ocean currents are modified by wind forcing events, eddies and waves, and to be able to meet all of our goals. Separately, we know that models have biases in the equatorial Atlantic cold tongue region. And so these observations will be crucial for validating those models and being able to assess reasons for why the models have biases in this region. Okay. And I should say that if it's not obvious, that's what the aqueducts look like when they were getting ready to be deployed during the February-March P&E cruise. Okay, so where in the world are we, in the world of currents, where are we deploying this mooring and putting these sensors? So here's 4 North 23 West, and this is a mean map of the zonal currents at the surface from a drifter climatology by Rick Lumpkin. So you see that the mooring is basically right between the interface between the south equatorial current, which runs westward, and the north equatorial countercurrent, which runs eastward. So it's a region of strong shear in the north-south direction, strong meridional shear. And that is going to be important later, so file that away. The TACOS instruments are also located north of the mean position of the equatorial Atlantic cold tongue. So this, what we call the cold tongue, is this big blob of cold temperatures. It's like in the Pacific, it's the analog of what happens during a La Nina event in the Pacific. So when you have cold temperatures here, it's like a La Nina in the Pacific. It's like those conditions in the Atlantic. So this is sort of a mean picture of the cold tongue. But as you see, you get these cusp perturbations that happen on the cold tongue front, on the northern front of the cold tongue and on the southern front of the cold tongue. And those are being made by tropical instability waves. And part of the mechanism that generates those tropical instability waves are the shears between, the meridional shears between these currents, the south equatorial current and the north equatorial countercurrent. Okay, so why do we care about TIWs? Hopefully you'll see why as we work through the talk. But TIWs not only perturb the surface temperatures, this is sea surface temperature, they also perturb the surface velocities by up to 1 meter per second, which is pretty big given that the mean currents here are on the order of 20 centimeters per second, or 30 centimeters per second. They have periods ranging from 14 to 50 days, and zonal wavelengths, the distance between these cusps in the undulations of the sea surface temperature front, are about 1,000 kilometers. And they propagate from east to west at about 20 to 50 centimeters per second. Okay, so that's the zonal flow. What does the meridional flow look like? The expected mean meridional currents in the upper 100 meters should be governed by the Atlantic tropical cells, which have wind-driven poleward flow. So this is showing you northward flow should be at the surface at 4 North and 23 West. And below that, you should have subsurface geostrophic equatorward flow. So if you think of this cell in the lower panel that's showing surface flow, downwelling, and then subsurface flow associated with the TC, you have southward flow below. So you should see at 4 North 23 West, northward flow at the surface and southward flow below that. But these currents, if you notice, the scale changed. Before it was plus or minus 50 centimeters per second for the mean zonal flow, and for the meridional flow, it's plus or minus 25 centimeters per second. These mean meridional currents are going to be likely about 10 times smaller than the perturbations you would see due to tropical instability waves. So that's why they're hard to observe when you take repeated transects of shipboard ADCP estimates, because they're many times aliased by the high frequency variability. Okay, hopefully, I don't know if everyone can hear, but I just had a message pop up that there was degraded audio quality, so hopefully that's okay. Okay. Okay, but we do still try. We persevere. We have these shipboard ADCP sections, and from them we can get a sense of what the expected mean zonal currents would be at 4 north and 23 west. So from this shipboard ADCP mean that was generated by Brandt et al., you see that you should be at the beginning of the north equatorial countercurrent, you should have in the upper 100 meters mean eastward flow between 5 to 10 centimeters per second. And it should be near surface intensified flow based on that study. However, this is based on 18 sections. So as I said, there's aliasing concerns. And because it's shipboard ADCP data and there's nothing in the upper 30 meters, you have to linearly extrapolate upwards from the surface using the surface drifter climatology. And you have to do that, you need to make an assumption that the vertical shear in the upper 30 meters is constant in time and space. Subsequent to that study, we looked at the meridional currents and made kind of the same map. And so if we look at 4 north, 23 west, what you would expect to see is, as I said, northward flow between 5 to 10 centimeters per second, and then subsurface flow of about 2 to 5 centimeters per second. And this was also based on shipboard ADCP sections. Here we have 36, which is good because these values are really small and the TIWs are very strong. So you need a lot to avoid aliasing. But we also had to linearly extrapolate upwards from 30 meters using surface drifter and Argo surface drift data. And make a constant shear assumption. And the spoiler alert is maybe that's not a great choice. And we're gonna hopefully learn that from tacos. Okay. So now we know historically what we expected to find. Now we know why we wanted to study it. We can now kind of make our way to actually looking at the data. But I jumped ahead. And before I move on, I just wanted to show you the vertical profiles that I pulled from those maps of the zonal flow and the meridional flow. And you can just see that what you would expect to see in the mean zonal flow is eastward flow in the upper 100 meters. And that doesn't agree very well with the 10 years of data that we have from the Parada Northeast Extension mooring at 10 meters depth. So maybe that extrapolation upward is not that great using an assumption of constant shear. In contrast, the meridional component, which is on the right figure, when we take the shipboard ADCP data and we extrapolate it upward, that actually agrees pretty well with the moored data. So this is what we have historically, what we know historically, and it's the context leading up to tacos. Okay, so what were the ambient conditions when we deployed? There's the mooring, and here it is on a map. Our cruise started down here in Montevideo and came up, and we did this 23 west transect, and then headed back to Charleston. And the mooring was deployed here in a time when it's seasonally warm, and it was warmer than average, and it was on March 6th. We have the shipboard ADCP section, so that's kind of a quasi-synoptic snapshot of what the currents look like during that cruise. And you see that where we deployed the mooring at the time that we deployed it, we were right on the verge between the north equatorial countercurrent and the south equatorial current in the upper panel. And there was subsurface northward flow. But again, we don't know what was happening above because we have this ADCP blind spot. Okay, the instruments have been in the water. They were deployed in March, but they've been in the water since then. So, we need to know what's the context in which it's deployed. What did it look like this spring and summer compared to other spring and summers? So on the left, you have the spring average, and then on the lower left panel, you have the summer average. And on the right, you have the values for 2017. And you might not be able to see the details. I think you can see it better in June, that this summer was warmer than average, and this spring was warmer than average. And the reason why we care about what's happening in spring and summer is that those time periods correspond to two coupled ocean atmosphere modes that dominate the variability in the tropical Atlantic. The first one is in the spring, and that's the meridional mode, the Atlantic meridional mode, and that's characterized by, it's an index characterized by the average temperatures in the North Atlantic minus the average temperatures in the South Atlantic. So that's one mode, and that peaks in boreal spring. And then the other mode, which is the one that I'm going to talk more about throughout this talk, is the Atlantic zonal mode, which is like El Nino in the Pacific. Unlike El Nino, which peaks in the winter, this mode peaks in boreal summer. And the index for that is the average. This is like the Nino 3.4 index. It's the average temperatures in this equatorial box. And so you can kind of see by looking at this, but I'll show you on the next picture that it's so, that it was warmer than average for both of those seasons. Okay, so this is the actual indices themselves, and you see, yes, okay, in 2017 in spring, it was slightly, the AMM index was slightly positive, so we had a warmer than average North Atlantic in the spring. This lower panel shows you the zonal mode index, the ATL3 index, and you see in the summer, yes, it was warmer than average. So we had an anomalously warm cold tongue in the summer. Because of previous studies, when we have this anomalously warm cold tongue, we expect to have a weak tropical instability wave season. We had found this anti-correlation in previous studies that when this is positive, you have weak TIWs. When it's negative and you have a cold tongue, you have strong TIWs. And that's the reasoning, the mechanism behind that is that when you have weaker trade winds, you have a warmer cold tongue, but when you have weaker trade winds, you have weaker currents, and so you have weaker shears. And so the mechanism that generates and sustains TIWs, which is those shears, is also weak. So that's the link between warm temperatures and a weak TIW season. Okay, so now that's the backdrop of what we know and what we expected to find, and now we can talk about what we actually observed. So these are the surface currents that we observed with tacos. So this is the near surface flow at 12 meters depth. Red is showing you this year's deployment. So this is the PNE sensor that was deployed this year at 12 meters depth. And then because this depth was observed for the last 10 to 12 years, we have years and years of data. And so this is showing you the evolution as a function of day of the year. So gray is all the years of data we have at this depth, and black is the average. And so to the eye, you can see that what we're observing this year is not that different from what we've observed in years past for the zonal component of velocity. And the means, so the mean zonal circulation at that depth is 5.8 centimeters per second, and the mean northward flow is 2.5 centimeters per second. And because we have that long-term record, we can say that those means are about half of the long-term means. And if we think about, okay, well, maybe there's seasonal aliasing, maybe because we're not capturing the full year, that's explaining some of that difference. When I look at that same time period from the 10-year record, that explains part of the difference, but not all of it. So maybe this year is just a weaker current year. So something to think about and figure out why that is. Okay, the other thing that you see is that during the TACOS deployment, we captured these three large 30-day fluctuations in late spring and summer. And we also have these kind of smaller perturbations in the second box that are about 5-day timescales that develop in the fall. And they're much larger in the meridional component of the velocity than they are in the zonal component, which is kind of different from what we've known from the equatorial region. Usually in the equatorial region, right on the equator, the story is all about the zonal currents. And here, what's fascinating and interesting is that the story is about the north-south currents in terms of the variability. Okay, I think that's all I want to say about that. And now I can show you the vertical structure, because that's why we put all of these moorings out there, to learn about the vertical structure. Okay, so this is now looking at the same thing, the zonal component and the meridional component with depth. And so you can see that those perturbations have a surface all the way down to 87 meters signature. At the surface, you have amplitudes as large as a meter per second, and down to 87 meters, you have amplitudes as large as 70 centimeters per second. And so you can see that structure. You have northward flow, southward flow, northward flow, southward flow, and the values, they're the same scale. Usually we plot meridional velocity on a different scale than zonal velocity. They're on the same scale, and meridional velocity is dominating. You also see these, I'm not really going to talk about these 5-day fluctuations because I think they're wind-driven, but I still don't know the details of that. But you can see that those don't extend as far down, and they're weaker in amplitude. The other thing which you might be able to see is that I've put gray dots on here. And so one of the exciting things about this data set is sometimes we put current meters out there and they fail almost within a week or a month. And these are still out there and they're still reporting data. The only one that has failed about halfway through the record was the 37-meter depth sensor. And so we're just interpolating across that gap for the rest of the data set. But when we compute a lot of the statistics, we don't do that. So this is just for visual comparison. And then the 87-meter sensor quit about halfway through. But all the other sensors are still reporting, and we get the data in real time. We get hourly averages once a day. So it's a really amazing data set. The other thing that I want to point out before I leave this figure is that the black line is the depth of the maximum shear squared. So I took du dz and I squared it, added to dv dc and squared it, and then looked at the depth where that was maximum for each time. And this is a 4-day low-pass filter, so if I actually put the hourly values, it'd be very noisy because there's a lot of high-frequency variability in that depth. But this gives you a general sense of what's happening. You see that it was the shallowest in the spring, and then as the tropical instability waves came in the late spring and summer, the depth of the maximum shear increased. And you also see that when you're in the northern phase of the TIW, you have a shallower depth, and in the southward phase, a deeper depth. So where the shear is maximum is affected by the tropical instability wave phase. Okay. So just to link, I don't usually think about the depth of the maximum shear squared layer. I usually think of things like the mixed layer depth or the thermocline depth. And so this is doing a comparison, and I apologize, the figure's a little messed up, but this is doing a comparison of the mixed layer depth, which is the black line, computed from the densities. From the Parada Northeast extension, we have temperatures and salinities concurrent with our velocity data set, so we can compute the mixed layer depth. And then we have the 20C isotherm depth in blue, which is an estimate of the thermocline depth. And so you can see that all of them started out shallow and they all deepened, but the timing was different. The red line, which is the shear squared layer, that deepened first, then the thermocline deepened in the summer, and then the mixed layer depth deepened later in the summer towards fall. So that's interesting. And there's also in the thermocline, you can see the 20C isotherm, the blue line, you can see that it's affected by the tropical instability waves. There's undulations in the thermocline depth. Okay, so that's the depth. What's also interesting is to look at the value of the shear at that depth. At the depth of the maximum, what is the actual maximum? And so that's what the black line is. It's showing you the maximum shear at each time. And so what's interesting is that in the spring, you have the strongest shear, and once those tropical instability waves start kicking in, the shear decreases. And there's an anti-correlation. The negative signs disappeared. There's a really strong anti-correlation between the value of the shear and the mixed layer depth, and the value of the shear and the isotherm depth. And then for fun, I broke it up into the two components. And so I looked at the dv/dz squared term, the north-south component of the shear, and the zonal component of the shear. And again, the surprising thing about this data set is it's the meridional velocity, the red, the north-south velocity that's really dominating the shear. So that's kind of different and new.
Surprisingly deep mixed layers, but how deep that.
Yes, I need to revisit this and recompute it with temperature, but I'll show you a salinity plot that I think will show you why that is. And I used the threshold that I used for the density difference, I think it was 0.07 kilograms per meter cubed. I need to maybe revisit how sensitive it is to that. And I also need to revisit it because the P&E sensors have much finer distribution of temperature sensors than salinity. And so maybe a temperature definition would not have as big of a jump as the coarseness of the sensors for salinity might be influencing that. So I need to revisit that. Okay, so that's the variability. Now we can look at the mean and compare those with previous values. And you see that actually our shipboard ADCP measurements look pretty good compared to the TACO's current meter values for the mean meridional velocity and zonal velocity. So that's shown here. You can see here that because that sensor dropped we lost some of the, the data stopped reporting about halfway through. There's a little bit of a jump, but obviously if I had interpolated across that, you wouldn't have that jump, but I wanted to just show what the actual value is. But what's surprising is that the surface flow is not strong. And what's strong is the subsurface flow. At 37 meters depth, you have 10 centimeters per second eastward flow and 9 centimeters per second southward flow. And at the surface, not that strong. And the shear, if you look in the upper 30 meters, there's not a constant shear. You don't see a straight line taking it from 30 meters to the surface. There's some is not constant with depth. Whereas for meridional velocity, well, we did pretty good with our shipboard ADCP values. But anyway, I just wanted to show you what the mean estimates were based on what we've collected so far. Okay, the other really interesting thing is that the mean shear, again, it's not strongest at the surface, it's strongest below 30 meters, and the dashed component is the north-south component of the mean shear, and that's what's stronger. So that's kind of the theme of the theme of the story. Okay, we don't have years and years of data, so we can't look at the seasonal cycle, but we can look at the seasonal evolution of what we've observed so far. These are monthly averages. And what you see is that the flow starts off pretty uniform with depth in terms of the direction of the flow. The flow is all southeastward, so eastward and southward in March, and then it ends the same way as it started. But then during this time period where you have TIWs, you have a sort of a two-layer flow in the upper 87 meters. You have a surface flow that's northeastward, so this is going northward and eastward, and a subsurface flow that's southwestward during April to June. If you look at the variance in each month, and this is showing you March to summer, and then it's kind of progressing through colors, what I just want to draw your attention to is that June and July have the highest variance, and they have the highest variance in V. And that variance is large all the way down to 67 meters. It's not only at the surface that you see large velocity variance. This figure pretty much tells you the same thing. I tried to partition into timescales greater than 1 month, 1 week to 1 month, so on and so forth. You see that in the meridional velocity component, you have, relative to the total variance, you have large variance all the way down to 67 meters in that 1 week to 1 month band. And again, the meridional velocity is just really, the dashed line is the variance of the meridional velocity at all depths for the total variance. It's just really winning out over the zonal velocity variance. Okay. All right, so we had this really high frequency variability on 1 week to 1 month timescales. I sort of said they're 30-day periods. I had computed them. I said, I think they're TIWs. Were they TIWs? And why would we have strong TIWs in our record when the equatorial Atlantic was warm? And previous indications would say if the equatorial Atlantic is warm, the TIWs would be pretty weak this year. These are some updated indices that we had computed in 2012 for tropical instability waves using satellite SST as a measure of the variability. And these are 2-degree bands at 5 north. So this is sort of like this is where Tacos is. At 2 north, where tropical instability waves tend to be pretty large, and at the equatorial band, where there's also a parata mooring at the equator. And I guess it's a lot of information here. I also overlaid the mooring data in red. So blue is satellite and red is mooring data. So this is what's happening at the Tacos mooring right now. So it looks like on average, 2017 is looking like a pretty strong year relative to the other years. It's not the strongest. It's not one of the strongest, and it's not one of the weakest. It's showing up as a pretty moderate to strong year for TIWs. Okay, further evidence of this, we all like to look at these XT plots that show the propagation of waves. So this is 2017. This is along 2 north as a function of longitude and time. And so you can see that there were a lot of tropical instability waves this year in terms of a sea surface temperature signal. And comparing to a year that was pretty strong, it's a moderate year. It's a moderate to strong year compared to a very strong year and a very weak year. You can see that there were a lot of TIWs and the amplitude of the sea surface temperature signal was pretty strong. You can see this signal in satellite SST data because you have a cold tongue front. So you have cold temperatures at the equator, and at 4 north you have warm temperatures. So you have a big temperature contrast. And as these waves move, you see basically these perturbations of temperature and salinity that are undulating past you. So it's a little bit of you can see it in SST because there's this big contrast between the temperatures at the equator and the temperatures to the north. But if we look at 4 north, where the mooring is, and this is the time of our deployment, we're even further north of the cold tongue front, and you can still see tropical instability waves. And it compares pretty well to our strong year. And it's obviously, you have much larger amplitudes than you did in that weak year. And what you see here, it's a little bit faint, but you see 3 TIWs that definitely went past our mooring. So those 30-day fluctuations that we saw at that mooring, you can see in the satellite record, and they show up propagating across where we have our mooring. Okay. So coming back to this thing about the SST index being positive, so our equatorial Atlantic is warm, and this should be a weak year. When we did this study in 2012, we used data up through 2011, looking at the relationship between the cold tongue temperatures and the strength of the tropical instability waves. And when we looked at 2 north and 5 north, we had a pretty good linear relationship. It looks like in subsequent years, there's a lot of outliers. And so the correlations, there was this anti-correlation between the ATL3 and TIW intensity, and it's still about minus 0.7, but before it was minus 0.8, minus 0.9. So it's decreased, and you have a lot more outliers, and 2017 was definitely an outlier year. So the relationships that we had established before have sort of changed. And so I'm not 100% sure why, but I'm trying to think about why that is. I have some hypotheses, and hopefully our discussion will lead to more hypotheses on why that is. Okay. One hypothesis that I had was maybe, if you held 4 north constant and you didn't change the temperatures there, when you have a cold year, the blue is showing you cold years in the equator, you would have a big temperature difference between the equator and what's happening at 4 north. And when you have a warm year, this shifts up, you would have a smaller difference. But it looks like, I don't think you can see it, but it looks like in 2017, we had warmer temperatures in the equator, but we also had really warm temperatures to the north. And so you still had a strong front. So you would definitely, with satellites, still see tropical instability waves because there's still a huge temperature contrast. And if you make a plot of the temperature contrast as a function of time, and then I color-coded it based on whether it was a warm year or a cold year. So 2017 was a medium warm year. It has as big of a temperature contrast as some of the really cold years. And in my head, before I made this plot, I thought it would be blue at the top of the image and red at the bottom. And it seems like it's really mixed. So I don't think temperature is the only thing happening. I think there are physical mechanisms like what's happening with the winds and what's happening with the shears that are also part of the story. So I didn't address this in full detail, but I revisited some of the calculations that I did at the time of the paper, where I looked at the strength of the wind stress divergence and the strength of the wind stress curl, which are proxies for the shear between the currents, which again are what provides energy for the tropical instability waves. And what I expected to find, and what we had found in this previous study, was that there was a strong relationship that when you have strong divergences in curl, the equatorial Atlantic is cold and you have strong TIWs. Again, like the same story that I showed with the scatter plot, that relationship is not holding as well, where we had this really strong anti-correlation between the wind stress divergence and SSTs and the wind stress curl and SSTs. Now we just have really weak anti-correlation. There's nothing, the story has shifted and changed. And one thing you can see, hopefully, I redid this calculation, which I had originally done with high resolution quick-scat satellite winds up through the failure of that satellite. I redid this calculation with NCEP winds, which are much coarser, and it's a model product that assimilates observations. But what you see is the curl, something that it didn't have before, has a decadal variability to it. And you don't really see a decadal variability in the SSTs. And so there's something happening with the winds that might be changing the nature of the relationship that we thought we understood 5 years ago, but maybe there's a non-stationarity to that relationship. Okay, so if we look at the winds themselves, these are the winds just to the north of the equator between 0 north and 3 north. You see that decadal variability, or maybe a trend, in the zonal winds, and you see that you have increasingly eastward anomalies in the wind, so it's a weakening of the trade winds. And you have some maybe decadal variability in the meridional component. So this is not conclusive proof. I would like to go back and do this calculation with a high resolution wind stress product. And I also want to look at Rick's updated drifter altimetry synthesis product to look at the actual shears between the currents where we can observe them, and really reevaluate this relationship between the trade winds, the meridional shear of the currents, the cold tongue temperatures, and the tropical instability wave intensities, because there seems like there's some decadal variability in the winds, and that relationship that we had previously established might not hold in this decade. Okay, but that is based on a model product. So you might say, how much confidence do I have that there's this decadal shift in the winds based on a modeling product that assimilates observations? We have at the 4 North 23 West a MET package, so we have the winds and we can look at them. And what you see is that in 2011, late 2011, early 2012, there's a shift, an eastward shift in the zonal wind anomaly and a northward shift in the meridional wind anomaly. So we only have here a 10+ year record, but there is an observed shift in the winds that corresponds to some of the shifts that I was seeing in the NSEP product. So this is to be explored in more detail. This is not conclusive. This is just some hypotheses I have and some supporting evidence for these hypotheses that needs to be further developed. Okay, so we have the currents, and because we have temperatures and salinities, we can look at how these variations that we saw from the tropical instability waves affect temperatures and salinities. And this is just preliminary analysis, but I wanted to put it up there because this is part of the motivation for why we've got the sensors there in the first place. We want to understand how this affects the temperature and salinity budgets in the region. Okay, so this is the temperature data set and the salinity data set. And so you can see, again, that deepening of the 20C isotherm, which is the black line. And getting back to Bill's question, this is what's happening with the mixed layer. You see that you have a very strong salinity signal here that is affecting the mixed layer depth. So what you do see in this sort of seasonal evolution that's modulated by a lot of high frequency variability is that the near surface becomes saltier and it becomes cooler as you go from spring to summer. And then the subsurface becomes warmer because the thermocline has been pushed down. And you also have fresh anomalies happening. And so this is just the actual temperatures themselves without any filtering. If I want to filter to sort of pull out the TIW signal and pull out the low frequency signal, so I remove the mean and I applied a 20-day low pass filter to the temperatures and salinities, you see that changing from spring to summer. It gets cooler, it gets saltier at the surface, it gets warmer, it gets fresher in the subsurface. And then you still see that where you have these undulations of the thermocline, you see cold, warm anomalies, and you also have subsurface salinity anomalies. And the fact that you have very weak signals at the surface. So remember, we were using satellites to tell us if the TIWs were strong. But at this location, the strong TIW signal is below the surface. And so you have very strong fluctuations here centered around 80 meters depth, not at the surface. And that's consistent with previous studies in the tropical Pacific, looking at mooring data at 5 North 140 West by John Lyman et al. So that they're near the thermocline isn't that big of a surprise. But that they have very little signal at the surface was, I think, for me, a little bit of a surprise. Okay, going along with that, you have a velocity evolution. So I can filter the velocities in the same way. And what you see is that there is a subsurface northwestward velocity anomaly. So you have subsurface flow that's going northward, and westward, and that will be important later. And then in the summer, you have the tropical instability wave fluctuations popping out. And again, they're stronger in meridional velocity. And what's interesting is that the southward anomalies are subsurface intensified. So they have a really strong signal in the lower half of the TACO's record, but the northward anomalies are surface intensified. Okay, so that has important ramifications for how it can move around heat and temperature signals. Okay, so we can take our first step at looking at heat fluxes by just taking the product of those two. So taking our T primes and our S primes and multiplying them by the velocity anomalies. So looking at the beginning of the flux terms. And so these are my last two science slides. I just want to show you that in spring, because of those currents, you have a strong northwestward flux of subsurface cold anomalies. And in the summer, you have tropical instability waves that are fluxing temperatures. And those meridional fluxes are large. There's compensation between the north-south component and the east-west component. But the north-south component is dominating in terms of the moving around of those temperature anomalies. Okay, if we do the same thing for salinity, the fluxes are weaker, or maybe my scale is just not a great scale. But what you see is that the currents produce a northwestward flux of subsurface saline anomalies, but it's a little bit higher up in the water column, and that has to do with where those salinity anomalies were sitting in the water column. And here you do have strong subsurface advection or fluxes of salinity, but you also have very strong surface fluxes of salinity. And again, the north-south component is winning out over the zonal fluxes. Okay, so to summarize, TACOS is providing us a novel, continuous in time view of the horizontal currents in the tropical North Atlantic at 4 North 23 West, which have an influence on the local temperature and salinity variance from the surface down to the thermocline. What I've convinced myself is that the empirical relationships between the ATL3 winds, shears, and tropical instability waves needs to be re-examined. We need to revisit it because the relationship between the equatorial Atlantic sea surface temperatures and winds might be influenced by decadal variability in the winds. What we've thus far observed from TACOS is that we have a rich temporal structure in both components of the velocity. The mean flow is largest in the subsurface, not at the surface. So the largest means were found at 37 meters, with values on the order of 10 centimeters per second eastward and 9 centimeters per second southward. And as I said, the mean surface flows were weaker than the long-term means. And then the other surprising result was that, unlike the right on the equator, where zonal velocity has the largest signal, here meridional velocity had a really strong signal, and the variance was larger in almost everything we looked at for meridional velocity. In terms of the shears, we saw that the vertical shears vary considerably over time. The depth of the maximum shear varies considerably over time. The assumption that the vertical shear is constant above 30 meters does not really seem to hold up. What we typically rely on to extrapolate shipboard ADCP data upwards, which is the best we can do since we don't have anything else, any other data sets to tell us what's going on between where the ADCP is cut off and where the drifters give us information about the surface flow. We don't have anything in between. Okay, and then we found that the maximum vertical shear squared layer was in the spring before the TIWs appear, when the mixed layer, the thermocline, and the maximum shear depths were all shallow. We observed 3 really strong, or moderately strong, I should say, 30-day TIWs, which we didn't expect to find in the first place because the equatorial Atlantic was warm, during late spring and summer, with magnitudes of up to 100 centimeters per second at 7 meters depth and 70 centimeters per second at 87 meters. And at the end of the record, we see shallow 5-day velocity perturbations, which I haven't really had a chance to look at, but I see perturbations in the winds that have that time scale. So I think it's wind driven. And then we saw strong subsurface temperature and salinity fluctuations near the thermocline, both before and during the passage of the TIWs. And it's likely that the horizontal heat and salt advection flux, the horizontal heat and salt fluxes, which I've only computed the first beginnings of by looking at the U prime T primes, may be larger than we expected. Okay, so our future plans In December of 2017, this year, Greg is going to be the chief scientist on a P&E cruise where they're going to turn over all of the moorings. And we don't presently have money for spares to do an at-sea turnaround, and we need to do post-cruise calibration on those sensors. But NOAA PMEL has graciously loaned us 3 to 4 aquadops, depending on how the cruise goes, to redeploy at 4 North, 23 West. And where we're going to put them is at 27 meters, 37, 57, and 87 if we get 4. And that's going to augment, again, the one that's always there at 12 meters depth. And so, you know, we might call that low carb or lean tacos, but the name is still pending. It might vary that a little bit. And then the plan after that is to take what we've learned from the full deployment, take what we've learned from the low carb lean tacos deployment, and then put the full array back in the water, or a reduced number of the instruments back in the water based on the insights from the first 2 deployments. That could be called smart tacos or smarter tacos or slightly better informed tacos. I don't know. We're working on it. So that's the plan for upcoming plans. And in case you're wondering, the reason why we picked those depths was because when we have this data set, so we can look at pairwise correlations between the various depths. And all my labels are gone, I apologize. These have labels that tell you what depths they are. But this is, you'll just have to take my advice that it's 27 meters, 37, 57, and 87. And for example, at the 87 meters, you see that that one is not strongly correlated with any of the other current meters. So that's providing us with independent information. So that's why we decided to pick that location. Similarly, 67 is not as strongly correlated with very many depths, so we picked that one. 37 meters was where we found the maximum shear, where we found the maximum currents. So we definitely wanted to capture that boundary between the surface flow and the subsurface flow. And then from 27 meters onward, they're all pretty well correlated in the surface, but we wanted to have some redundancy so that we really can understand what's happening in the upper part of the water column, and sensors fail. And so 27 meters is still pretty strongly correlated with what's happening at 12 meters, but it provides another transition between the surface and the subsurface flow. So that's why we picked the depth that we picked. Okay, and in terms of analysis, there's a lot to do because the data set is really amazing. We want to examine how velocity and vertical shear composites vary over a diurnal cycle, because we have, what we're getting real time is hourly data, but we will have even finer resolution than that when we get the sensors. So we can look at the diurnal variability of the velocities and the shears in the context of what's happening to temperature and salinity. And we can also look at what's happening over a composite tropical instability wave. So kind of following previous studies by Rio Inouye and several others that have looked at composite TIW evolution. I'd like to look more closely at the relationship between the equatorial temperatures, winds, velocities, shears, and TIWs, and try to understand why that relationship seems to have changed. And then I'd like to compute horizontal heat and salt advection terms and relate to the air-sea fluxes. And one of the questions that Greg and I have been talking about is getting at how do vertical shear fluctuations associated with the tropical instability waves help to modulate vertical mixing, which can affect the seasonal SST evolution. And that would follow on previous studies by Jim Moom and several others. So that's some of the ideas of where we're taking this after what I've presented today. So with that, I want to thank you for your attention. If you have questions that you don't get a chance to answer me, you can send me an email. I would like to take a moment to say thank you to Gustavo Goni, our division director, who provided the funding for these instruments, which we're so excited to have and learn from. And then our team here at AOML and CMIS that have helped me either purchase the instruments, get them in the water, they will be helping recover them. And I also want to thank Libby and Ryan and Chris. Libby and Ryan provided me early sensors that was like the precursor to tacos, and that gave us sort of the idea that it would be exciting to look at the shears in this region. And Chris Meinen had discussions with all of us about how we should cite the locations for the sensors. And then I want to thank the PMEL JASEO team, so Mike McFadden, Ken Connell, Paul Freitag, Stephen Coons, Ryan Wells, who helped get the sensors ready to deploy, put them on, deployed them, and we'll be recovering them. So I guess with that, I will stop and see if anyone has any questions. you.